Hey, hey, this is Steven from Legit Tech Tutorials and Steven's Classic Garage, and welcome to back to my Dyno video. So my Dyno development video. So we're not going to spend too much time in the on doing calcs anymore, hand calcs. We're going to start doing more of the Autodesk Fusion stuff. So I recently went to the metal shop and I found out that they have a couple more interesting pieces there that we could use as our roller. So if we go here to cars, go here to Dyno. So this is roller V1, so let's look at roller V2. So roller V2 I think is probably the max that we could go with. And that I found to be a 11 3/4 OD and a 1/4 inch wall. So that's way bigger. This one was 8.5 inch, I think. So this is 11.75. And a minus 0.25. And a 1/4 inch OD. Now, with this, oh man, I do not have my tape measure. Didn't I have my tape measure in here somewhere? Now with this, maybe do 2 foot right now. I mean, the minimum that I think that we could probably get away with 20 inches. Let's look at 2 foot. 24 inches. Yeah. Now let's take body 1, physical material, metals, A36, steel, and let's save this as roller V2. Okay, so let's do roller V1, open roller V2, and let's click bodies, body 1, this is roller V1, properties. Center of mass, moment of inertia at center of mass. I think it's LYY. But let's change this to inches down to foot. So now it should be in foot pounds. Properties, moment of inertia, pound mass per foot, LYY, should be LYY, I think. LYY. I'm thinking it's this bigger number. So basically you have one moment of inertia this way where this thing spins around, right, along the z-axis at center of mass, rotates around z-axis, and then you have rotate around the other axis, should be identical. So yeah, I think it's this one. I think it's this one, because this one, it should be this way is the same as this way. So basically this way is the same as this way. So the only other way is rotating on pivot around the axis this way. And then there's tumbling, but tumbling's the same difference. So here I'm thinking it's the 5 pound here. So again, we could do a simple calc. Again, I said we're not going to spend that much time in the simple calc, so we're going to do this quickly. It's 1/2 mr squared. Oh, 1/2 the O. I think it was like 1/2 this squared plus this squared times mass. So that is 11 3/4. This is going to be inch pound. You convert it into foot pound by dividing by 12. 11 3/4 squared plus the second one is minus half, so that's 11.25 squared. Quarter on that side, quarter on the other side. Now, luckily, I have my TI-84 here in the other room, so I'm going to go grab that really quick. Alright, so here's my TI-84. So let's take a look at it here. So 0.5 times, and what do we have pound mass here? Properties, and remember this is yeah, pound mass. Yeah, so should be good. 0.5 times 46 pounds. 0.5 times 46 pounds times A squared, which is 11.75 squared, plus B squared, 11.25 squared, and then that divided by 12. Okay, so let's try this old-fashioned way. So here's a tube section. Oh, okay, so apparently you need a membership to do that. Interesting. Okay, let's try this one. Units, inches, D is 11.75. Small d is but remember, this is not the so this is this times basically then you have the mass, so it's basically this times the mass, right? So in this case, this is on y. You see it says IY. Okay, so y is 1149, z is, well, basically it's rotating either this way or this way, so it should be the same, 150. So it's 150, that should be already multiplied by half, times the mass, which is 46 pounds. And this is in, oh, this is inch cubed. Oh, right. So we have to do way more to bring that down. So that is probably correct, because then you have to 12 times, yeah. So that is probably correct, to take it down from 6,086 down to foot-pounds. So let's do inch cubed to foot, or this is to the fourth. Double square, I guess you could say. Double square inch 6086. Yeah, so okay, so yeah, weren't we doing this in the other one here? Let's go into Swift Calcs. Jump back into Swift Calcs again. And with Google, and it said that my thingamajig is about to expire, so what I might do is I might create a whole bunch of worksheets, because once you, oh, I guess it already, okay, so mass. So basically, let's change this now. So this is 11 3/4. That's fine. And this is 11.25. So let's just go high on this one. Okay, length 24 inches, that's fine, okay. 62 pounds. Okay. It's possible that it's this here, because this is a little over. Okay, so 2,000 inch pounds. What? Foot. 14 foot-pounds. Square foot-pounds. Dual roller moment 4,001, whatever. Okay, so basically now we've doubled it pretty much, but we've increased it quite a bit. So now we can do a couple things. Number one, we could drop the length. So again, the maximum tire that I'm probably going to run is 300 millimeter 2 inches. It's probably 15 inches or so. So let's say that this is 15 inches. Or even, let's say, 1.5 feet, so that's like 18 inches. Oh, we could go 15 inches. That's another like 1.5 inches on each side, pretty much. So now we are down to 38 pounds, let's say. 2 rollers, that's 48, that's 77 pounds. Now, what we could do is we could add flywheels on it, right? Now here's the deal. Can we actually calculate this here? What was it? Mass here, foot-pounds moment. Okay. So, oh, this is roller 2 now. Properties. Oh, this is ounce-pounds. I changed the... foot-pounds. Foot-pounds is 9. Pretty close. So yeah, it's a smaller number. Now, basically it's saying 9 because it's quite a bit longer. Actually, I haven't changed the length back, so let's change the length to 15 inches. 15 inches. Not what? Oh, 15 feet. No, 15 inches. 15 inches. Okay. And then now what is our properties here? So, moment of inertia. Yeah, pretty close. 9 something. So here I have 8.99 foot-pounds in our calculation. Right here. So pretty close. Obviously what happened is this is, this is higher and this is higher and this is higher. So probably also that and the density, they probably have two different densities. So really, really close. Somewhere in between these two. Actually, no, right here, the smaller one, 8.926. So yeah, basically it's because my bigger one is higher. So let's see if I could change it, because you could type it into this spot. And then what I could do also is I could do oh, they got rid of the little gear cog to change the things on here, but yeah, we'll have to go with that. But 11 3/4 by 11 1/4. So with those two, we'll have pretty much a really close number. So again, it's this one here. So with this out one smaller and the inside one a little smaller, it'll probably get right in there. Because here is 8.99 and here's 8.826. So it's definitely the smaller number. Okay, which I agree with. It's going to be the smaller number. It's going to be way easier to roll it this way than it is to rotate this thing with respect to the center of mass. Alright, so we got that figured out. So now we can do it in CAD. We just look at this LYY. If it's orientated this way, the front here, but it's just basically a small number. Because rotating this way and then rotating this way is the same. So you're going to see the rest of them will be the same number except for 2, which is rotating this way, rolling, and then I guess rolling the other way. So rolling towards the Y or something, rolling through the Y, and then this is rolling through X and Z or something. And X, Z. So yeah, XZ plane. Oh, XZ plane. Okay, so this is through the YY plane. So spinning around the YY plane. This is the XZ plane and the ZX plane. They're just flipped. Okay, so these are different planes. That's why XX. So this is the XX plane. So spinning about the XX plane. And then spinning about the XY plane, right? XY plane. XY plane. This is the YY plane. I don't know how you could have a YY plane, but that's okay. Alright, so I get it. Well, basically we did it by process of elimination. It's this one right here. Alright, so now what we want to do is off of this, now that we have a good mass on here, and let's see the mass changed. Mass is 38 pounds and 38.42, and here we have 38.83. Obviously it's going to be higher because again the outside's big, so I think we got it dialed in. So now that we have that, we see that we have a moment of 9, dual roller moment of 2.6, right? 9 foot-pounds and a dual roller of 2.6 inch squared pounds. So what we need to do next is we need to add some caps. So basically what I want to do is I want to add a cap here, a cap in the middle, and a cap at least on the outside. Basically I want to get from here, which is like 40 pounds, to 120 pounds. So to 120 pounds each. So of course we're going to have 2 rollers. So we're at 80 pounds right now, so we need another 40 pounds. So we're going to do that in flywheels. Now, what size flywheel are we going to get? We want to add some strength, so probably do a 1/2 inch flywheel. So let's go ahead and look at a 1/2 inch flywheel. So let's go ahead and create, not in this one, no, let's create a separate component. And then this is 11 1/4 on the inside. 11.25, and then this is going to have a hole in it for some sort of shaft, and we'll have to also look at the shaft. So this is going to change as time goes on, because we're going to have a shaft in here, right? So that shaft, I don't know if it's going to have to be 1 inch in diameter. 1 inch is probably big enough, but really it's going to be determined by the load, and obviously that load is split between the 2 rollers that go in there, either roller V1 or roller V2. But right now I'm going to say we just have, oops, we don't need a second sketch. Let's just say that we have a, let's just say that this is the flywheel, because on the other calculator, I believe that that speed calculator, it doesn't give us really that option. And again, this is probably the biggest roller that we could go with, because the lathe that I'm cutting it on will probably only go up to that. So let's go ahead and save this, and let's call this cap. Cap V1, and then we'll have this one, and then we'll call this roller layout. Roller inertia test assembly, and then we're going to roll in a roller V2, and I think we're going to try, well, let's go back here, let's see what this weighs. Oops. Oh yeah, what is the physical material? Steel. $836. Update. Okay, cap. Properties. This weighs oops. Oh, I think I hit the back button when I did that. This weighs 14 pounds. Ooh. So we need 40 pounds. And again, increasing the mass doesn't really help much. And if we put that, I think we'll be okay with the regular disc, because then we only need to reach in 7 inches. But if we could add 4, we could subdivide it into 4. Because again, if we add thickness to it, we're not really going to gain much. So if we add 4, but we want the diameter, so we want to limit the thickness, but to the point where it's going to contribute to the strength of it. So 15 pounds, let's say, times 4, that's 60 pounds. And we are already at okay, so we're already past. So 30, that's so let's say 3, that's 40. 3 is 45 pounds. 40 pounds plus 80 pounds. That's 120. That's 100 and So 35 pounds, that's 115 pounds. That's perfect. Plus, well, then we need to have the other stuff. Then we need to have the shafts and stuff like that. So, but this guy's going to have some holes cut out of it, so we'll get some of that back. And then that way we'll have a maximum, we could load another 10 pounds of stuff onto it, or more, because we're going to cut these out. So maybe these are only 12 pounds when we're done with it, and then we could load it with other stuff. And then we'll be around 130, 140 pounds for the whole thing. But we want most of it in the inertia, to go towards the inertia. Okay, so, perfect. Now, let's go ahead and joint. So now basically what we need to do is we need to do a little bit of math. So we go here, and then we go here. So now it goes on the outside. This thing is 1/2 an inch thick. This is 15 inches. 15 inches. So we need to straddle that 1/2 inch. So we're going to cut off. So it's 7.5 inches, right? So we need to go in an additional 1/4 inch. So 7.75. So minus 7.75. Oops. Not that way. And this way. Okay, so it's in 7.5 inches, which is 1/2 of 15 plus an additional 1/4 inch. So now that is in the middle. Wait. Oh, I forgot to save. Oh. Now it's in the middle. Okay. Now let's add cap V1, another one. Let's go ahead and join it there. And let's joint it there. Okay, so now let's check here, physical properties. Let's change it to document settings from inch to foot. Properties. Moment of inertia at center of mass should be right in the center. So this should be the small one, 13.472. 13.472. So we went up from 9 to 13. So we increased the mass. Oh, we only have 80 pounds. That's strange. Oh, because it's, oh, so that's 160 pounds. What? 1, 2, 3, 4. Oops. Okay, so we added another, okay, so now we're at 80 pounds. That's not going to work then. So we can't have that middle one. Basically. But how's that possible if this one's different? It's a 15-pound mass. So that's 40 plus 3 is 345. So yeah, 45. So that's right. So we can't go with that middle one then. So let's go here. Because now we're way too overweight now. There we go. Okay, so now properties. Now we are at 66 pounds. That's cool. And we're at 12. So we went up another 4 or so. So now let's say that over here Okay, so basically what we need for adequate on the Mustang, we need 186 square foot pounds, and right now we're at 12. So also another thing is that we have technically 4 of these, because we got 2 on the front, we got 2 on the front, we have 2 on one side and 2 on the other side. But if it's one-wheel drive, we're dumping all the power on one side. Right now the Mustang is one side. It's only one-legged. There's no posi. So that's another thing, is that it's only limiting it to one side, which is not very good. So, well, let's say that this was 4-sided. So let's say this 12, that's still 48, and we need 186. So we need another 4 to 5 times. So now basically we have a couple options. We need to absorb, we're going to need to do more than the inertia, or we're just going to have a slower pull, like a 10-second pull or like a couple second pull. So let's see if I have my stopwatch here. I mean, 10 seconds, that's a long time. So let's see, let's go to the... So let's go to the Dyno builder again. Wait a second. Dyno Sizer. Yeah, there it is. Okay, inertia Dyno Sizer, and then we're going to find this one for, let's just do, so 9, let's just do 18 for right now. 18. So this one, we just need 18 here. So here. Okay, 11.2 by 5.9. Okay, we're not even up to 1 second. Okay, so we're definitely going to need to find some way of absorbing the rest of the horsepower, right? So we have inertia dyno, that's good, but we need some other way of doing that. Otherwise we need some sort of giant ring, some sort of huge ring that will be just too large and too heavy to move around. So we're definitely going to have to rethink the project here and do some research and try to figure out how we are going to do that and how we're going to make it cheaply. So this is basically, we're at the limit of what we can do inertia wise. Now we need to figure out how we could do it with some sort of technology. Now we do have some ways of burning it, as far as doing some sort of air pump or water pump or something like that. But we need to figure out a way of doing it maybe with a motor, so we could do electricity, so we could tell how to, so we could get it really, really accurate. Alright, so that's basically it for this video. We've bumped it up a little bit to almost a second with 200 horsepower, but if we did with my Rabbit stock, would be 2 seconds, and probably after my modified Rabbit, it's about 1.4 seconds. So we need to keep working and figure out how we're going to dissipate this energy. So thanks for watching. This has been Steven from Legit Tech Tutorials and Steven's Classic Garage, and I'll see you guys in my next video. Take it easy. Peace.